Thanks. Sorry about that. So I graduated recently from MIT Computer Science, and happy to be here. Thanks for the opportunity to speak. So the basic setting for this talk is going to be a rather general framework for posing combinatorial problems, namely that of constraint satisfaction problems. And just for clarity, I'm going to focus on two CSPs, which are constraint satisfaction problems in which every constraint involves at most two variables. So in this setting, we fix some alpha bit, sigma, which you can think of as being of constant size. And the input to this computational problem is a graph, G, where every vertex has an associated variable that's to be set over some value from sigma. And every edge is not just an edge, but is also a constraint on the two endpoints of this edge. So it tells which of the allowable assignments of the endpoints u and v are satisfied by this particular edge constraint. So as a hopefully familiar example, you can view three coloring in this way. So we're given a graph, G, and we want to color it with these three symbols or colors in such a way that the edge constraints all say that these adjacent nodes have different colors. And a solution to a CSP is just a variable assignment that satisfies all edges. So in this case, it's a proper three coloring of our graph. So from the computational complexity standpoint, our main interest is in whether we can efficiently solve these CSPs. Say in time polynomially bounded in the input size, which as a proxy you can let n be the number of vertices in the input graph. And by solve here, I just mean return a solution if one exists. Otherwise, just output that no solution exists. So we're not asking you to do the impossible, just to solve the problem if it can be solved. Well, you probably know that this, even the three coloring example that we saw, is NP complete. So this question is equivalent to P versus NP. So at this point, we're out of our depth in trying to understand this question. But we're willing to at least take P not equal to NP as a plausible hypothesis and see what else can grow out of that belief. So the consensus guess in the community today, I think, is that probably P is different from NP. And in the worst case, these constraint satisfaction problems are very hard to solve. And there have been many approaches to sort of bounce back and try to get around this difficulty in practical settings. For example, approximation algorithms are algorithms which return approximate solutions which try to satisfy most, if not all, of the constraints. Heuristics are heuristics which work well in practice even though we don't understand why and which might fail on pathological examples. And average case analysis tries to give algorithms which succeed under some natural input distribution. These are all ways to say, well, just a second, maybe constraint satisfaction problems are not as hard as all that, but in practice they might be solvable. And I'm going to talk a little bit about a different approach to coping with interactability. And this is known as preprocessing or kernelization. In this approach, we're given a complex input instance, and we're going to try to simplify it to something that's of a more reasonable size, so that once we've simplified the input instance and sort of boiled down it to the essence of the problem, hopefully eliminating vertices and so forth, then when we apply the brute force algorithms that we know today for satisfiability of these problems, we incur less exponential blowup in our running time. So what kinds of simplification can we hope to achieve in general? Well, a seemingly modest task is, given an n-vertex graph, just try to shrink it by one vertex. So suppose we could do this. Suppose that we could just reliably take an n-vertex graph and shrink it to an equivalent instance of size 1 less. And here by equivalent, I mean that the new instance has a solution exactly if the old one does. Well, we could then iterate this problem until we ended up with a baby-sized instance, and we could solve that by hand. So this would actually allow us to decide CSPs in polynomial time. So this seemingly more modest goal is not as modest as it looks. And this suggests that for preprocessing techniques to be successful, they have to make some kind of optimistic assumptions about the structure of the input that they're given. Okay, so we have to leverage some kind of underlying simplicity in the instance in order to achieve simplification. or shrinkage of our instance. And so actually, these preprocessing algorithms have been given for many special cases of important NP-hard problems. And this is, I think, one of the algorithmic success stories for NP-hard algorithms. And I don't have time to describe a real example, but let me give you a toy example of the kind of things that we can do. Suppose that we're given a constraint satisfaction problem where basically almost all of the vertices have degree 2. Okay? So there's some parameter k, and only k of our vertices are allowed to be of degree 3 or more. So here's an example. We have these basically 5 important nodes, and then these many intermediate nodes, which are of degree 2. And the claim is that we can efficiently take an instance like this and convert it to an equivalent instance where we now only have k vertices. Okay? And this is just a matter of observing that this sequence of constraints between intermediate vertices here can be efficiently converted into a single constraint involving only the 2 endpoints. Just a sort of basic exercise. So we get something that looks like this. So that was a small success. This parameter k, which is sort of a feature of the input instance, was translated into a size bound on the output instance. At the same time, we've encountered other simple cases that have resisted our attempts at preprocessing. So let me give you a not-so-toy example. Suppose that we're given a CSPG that has the structure of a grid, okay? A k by n grid, where k is, think of it as very small compared to n. And really, the grid structure is not too important here. What matters is that we're imposing a natural bound, which is a bound on some notion of the width of our graph. So we have a long but narrow graph, and we're wondering whether we can somehow leverage this narrowness to reduce the problem's complexity. So as an example of what we might hope to do, could we, analogously to the previous example, could we hope to reduce this to an equivalent grid instance on something whose length was now proportional to k? Right? This would be great if we could do this. But we'd even be willing to settle for reducing to any constraint satisfaction problem of size governed by some polynomial in k alone, and not by this larger parameter n. We would still allow ourselves polynomial in n pre-processing time, but we would want to end up with something like this. This would help us greatly. So in this really influential work of Bodlinder, Downey, Fellows, and Hermelin, they conjectured that even special cases of this grid reduction task are intractable for polynomial time algorithms. And what they showed is that, or what led them to this idea is that the observation that many other natural instance reduction or pre-processing tasks are at least as hard as this task. So if certain special cases of this task were hard, then so would many other problems. And this would give kind of a unified explanatory framework for the hardness of many pre-processing tasks that we've encountered in the literature. So it's nice to introduce a new hypothesis and show that it bears fruits in seemingly different problems, but we still have kind of a problem of proliferating assumptions in complexity theory. That is, we have all kinds of questions that we'd like to more closely relate to each other, since given that our field is almost defined by these uncertainties. So can we somehow boil down this question to something more standard? And in work of myself and earlier of Fortnow and Santhanam, we showed that indeed this can be done. So the particular special interest, the special cases of this problem that are of interest to algorithmists, this grid reduction task, are indeed hard unless we have the following containment of complexity classes. And you can think of this as saying that there exists a surprisingly powerful, even awesomely powerful system to disprove or prove the unsolvability of CSP instances. Okay, so to give a short refutation of the solvability of a given CSP instance, with the only caveat that we need some kind of polynomial amount of non-uniformity for a given input size. So it's a powerful proof system, but it requires a little bit of additional help. But these things are still considered unlikely to exist. So this kind of ties this question into more standard and well-studied issues. And my contribution was firstly, to expand the set of special cases that we know to be hard under this assumption, and secondly, to expand the classes of algorithms against which these tasks are hard, to include probabilistic algorithms, and I also gave some evidence against quantum algorithms, although I won't go into that. Okay. So following up on this, what are some next questions that we could think about here? Further questions include, and I'm not the first to ask, at least the first one. First, what kinds of graph structure account for the difficulty, the computational difficulty of 2 CSPs? And second, and I'll expand more on this, what kind of structural transformations on CSPs are efficiently performable if outright reduction of size is not always feasible? What can we do to sort of modify a CSP? So there's been some prior work on this question. There's a notion of tree width of a graph G, which is some measure of its fatness or distance from being tree-like. This is just a picture stolen from Wikipedia, but briefly what this asks is, if we want to sort of flatten or embed G onto a tree in such a way that all connections are preserved, what kind of maximum congestion do we need to incur within these nodes of the tree? Okay. So tree width was identified as a very powerful property of constraint satisfaction problems that can be exploited by algorithms. Namely, we know that many NP-hard problems, including all 2 CSPs of the type that I've talked about here, can be solved in time n to the O of k on an n-vertex input graph where we're given a tree decomposition that witnesses that the tree width is at most k. Okay? So it's an exploitable property. And furthermore, from the complexity or lower bound side, Daniel Marks, building on earlier work, had a very interesting result. He said that let's take any family of graphs where Gn has size n, is on n vertices, and all of these graphs have at least some value k, tree width. Then assuming a certain hypothesis called the exponential time hypothesis, we can't even hope to solve CSPs whose structure is restricted to come from this family G in time that's too much less than n to the O of k. Namely, we can't do it in time n to the little o of k over log k. Now, the exponential time hypothesis is just a hypothesis that says, roughly speaking, NP problems are very hard. They require time that's exponential in the worst case. So we've taken this assumption about the worst or the hardest instances of NP problems, and we've translated that into a statement that says that basically any family of large tree width graph structures can embed or encode a set of hard instances where the degree of hardness is related to this tree width parameter. So I think it's a very satisfying connection between a graph theoretic property and a complexity property. Now, moving on to this second question, I would like to build on this work and ask about what kinds of structural transformations we can perform in polynomial time. And here's the notion that I'd like to explore. I'd like to say that for really hard graph instances, CSP instances G, not only can we not shrink G outright, but we shouldn't even be able to deform the essential structure of G too much in polynomial time. A bit more formally, suppose that we have some efficient algorithm, A, that always takes an input graph G and sends it to a satisfiability equivalent output graph H, so it has a solution exactly if the input has a solution. Then I'd like to show that, well, maybe it succeeds in solving certain instances, but at least on some worst case inputs, I'd like to show that the output instance H is essentially just G, the input instance, in disguise. At least on the graph structural level, I'd like to say that H contains a copy of G. And more specifically, I'd like to say that analogously to tree width, I'd like to say that this output instance H contains a copy of G that's embedded into H with low congestion. We have to be a little bit careful here. There are certain instances like a cycle set of constraints, which can be solved efficiently, or a set of constraints on trees. So we should actually, to make this seem plausible, we should allow H to sort of grow a tree out of any vertex or to subdivide its edges. So we should allow subdivisions and these tree growths. But after that, I don't see why this conjecture might not hold. I would say that it's a working hypothesis rather than a firm conjecture. I'm happy to, tweak it in light of new evidence. So some possible tools to establish this would include approximate min-max duality. This is a tool used by Marx. Essentially, if we want to say that if this new graph H does not contain a copy of G inside of it, then we should be able to identify some kind of bottleneck, information theoretic or communication bottleneck between the nodes of H, and that would translate into some kind of bottleneck on G that we could then exploit to solve G more efficiently than brute force. There might be some communication complexity tools that could be leveraged in this project. I'm willing to make any kinds of plausible complexity theoretic assumptions. So this is, even though this is a much more, ambitious statement than P not equal to NP, I'm trying to say that, really hard NP instances are irreducible in the sense that you can't even get rid of their essential structure when you attack them in polynomial time. I'm willing to assume anything reasonable to get this to work. And I'd love to hear new ideas from anyone at IAS. So thanks for your attention.